at this point, we've talked about the different forms of quadratic functions, the graphs of what they look like, axis of symmetry, stuff like the vertex, and the y-intercept. But one thing that I haven't talked about yet is what about the x-intercept or x-intercepts, and how do we find those? And if you recall, well, we did talk about the basic idea, which is, well, the x-intercepts always occur when f of x is equal to 0, or if I were to plug in 0 on the other side. So, like, looking at some of the previous examples, if we wanted to know where it crosses the x-axis, we could always start by setting 0 equal to x squared plus 4x plus 5, and we would then want to know, well, where does the quadratic function equal 0? Or, we often refer to this as a quadratic equation. And that's kind of what I wanted to review next, is how do we solve quadratic equations, and what different methods are there for that? So one of the more standard methods is by factoring the polynomial. But as you probably remember from algebra, a lot of polynomials, we call them prime polynomials because they can't be factored. And actually, one thing we're going to talk about in chapter 3 is technically there's no such thing as prime polynomials when you're talking about certain types of numbers, but when you're working with real numbers, sometimes there is no way to factor them. And just to sort of review what I'm talking about with factoring, that means I'm trying to find ways of writing a polynomial such as this, where it will factor as x plus something times x plus something, or plus or minus, whatever it may be. But sometimes we might recognize that it is impossible. Like, remember, the goal is to make sure that the two numbers out here add up to 5, and that they, assuming it's just x, the two numbers here multiply to 5 and add up to 4. And when there is a leading coefficient, it's a little bit more difficult than that. But in this particular case, well, to multiply to make 5, there's only one way to do that with whole numbers, and that's 5 and 1. And that might be a good first guess, but notice that, well, 5 plus 1 would add up to 6 doesn't quite match when multiplying it all out by the distributive property. And another guess might be, well, maybe if that doesn't work, maybe we could do 4 times 1, but remember, that's not going to work either, or 3 and 1. But we can quickly come to the conclusion that there are no two whole numbers that work to factor this polynomial. So the question being, well, how would I solve the quadratic equation in such cases? Well, that's where we can rely on the quadratic formula. So much like the vertex formula exists to find the vertex of a quadratic, we can use the quadratic formula, which is on the last page of this packet, quadratic formula to find the x-intercept. So this is just something to review. A quadratic formula is useful for solving a quadratic equation, but that's also the same as finding the x-intercepts, because notice that when I've set something equal to 0, that's a synonym basically to the x-intercepts of a graph. Or we sometimes also call them the roots or the zeros. So let's look at a couple examples and apply the quadratic formula to solving quadratic equations. And in this case, also the question is, well, why does a quadratic formula work? It cannot, like formulas in mathematics, can often, sorry, my dog is barking, can often seem like magic, and where do they come from? And that's we're going to do that in class time this week, and I want to discuss that train of thought. But for now, we're just going to believe it, and we're going to pretend that we for sure know this exists. But actually, this formula can be generated by completing the square, as we did in the previous page. But let's do a couple examples of solving the x-intercepts by quadratic formula. And actually, before I begin, I wanted to return back to the lecture slides and talk just a little bit about the quadratic formula and its position. And one thing I wanted to review about the quadratic formula, which is the component which we refer to as the discriminant. The part which is inside the square root is often called the discriminant because it helps you to determine how many x-intercepts there will be. When it is a positive number, what the formula will result in is something plus or minus a positive number, which means there's going to be two answers. If the discriminant is equal to 0, that means this whole thing will become 0, and you're only going to get one answer for the discriminant, which is just negative b over 2a. Sorry, just for the root, just negative b over 2a. And if the discriminant is negative, then we run into that same problem when we were talking about domain before, where there is no real number, which is the square root of a negative, and that results in no real zeros, because if we get an imaginary number, that means it's invalid, and imaginary numbers do not show up on the graph. And again, we're going to talk more about imaginary numbers in chapter 3 a little bit later. That all being said, if I was to try to solve it, I could first begin just by writing down the quadratic formula, and it's always as easy as that. So x, the solution to such a quadratic equation, is equal to negative b, negative 3, plus or minus the square root of b squared, which is 9, divided by 4, or sorry, minus 4ac, which is 4 times 5, 20. And that's going to be minus 20, and that's all over 2 times a. A is 1, so that would leave me with 2. And this is exactly what I was talking about in that example, where when you have a discriminant, notice in this case we would get negative 11. And for now we're just going to leave it alone, but we will review how you simplify this in chapter 3. Basically, I'm going to get a non-real answer. So what this means is that the equation has no real solutions. And the conclusion is that this quadratic function from right here has no x-intercepts. And we've seen examples of parabolas that don't cross the x-axis, meaning they don't have x-intercepts. So if we were to graph that quadratic function in our calculator, x squared plus 3x plus 5, we can see that it does not cross the x-axis, and that is consistent with what we're getting as we're applying the quadratic formula. And I'll go ahead and zoom back into the standard window just to put it in context like that. And this is a common result with the quadratic formula. Though sometimes you have quadratics that cross the x-axis, like if we were to look at this quadratic and graph it, negative 3x squared minus 6x plus 24. Sometimes quadratics do cross. And if I'm looking at the graph, this is actually another way you can solve a quadratic equation, is by graphing, setting it equal to 0 and graphing it. And actually you can solve not just quadratics, you can solve almost any equation by doing exactly this method, graphing it and looking for the x-intercepts, which is basically relying on our calculator's ability to graph anything and basically figuring out where it's 0. But notice it appears to be negative 4 and 2 as our x-intercepts. But let's just, since the point of this video is to practice with the quadratic formula, let's do one more and see what happens. X is equal to negative b. Remember that when b is a negative to begin with, that would be negative 6, which is positive 6. So how I like to remember it is change the sign on b. Then it'd be plus or minus the square root of b squared, and that should always be positive because b is negative 6, then squared is 36. Minus 4ac is minus 3 times 4 is 12. 12 times 24 is 144 times 2 is 288, I believe. I'm going to go ahead and double check that one because I'm quite tired again. Sorry, I'm always tired when I'm recording these. I don't really have much option. It is what it is. And yeah, there we go. Negative 4ac is 288. And that's all over 2 times a. A is negative 3, so that would give us negative 6. And this is how I like to solve the quadratic formula. I like to plug in each little group, simplify, and go from there. So simplifying the discriminant, which again is just the name for the inside of the radical. Another term for an inside of a radical in general is sometimes called the radicand. Not that that's important. Discriminant is specifically with regards to the quadratic formula. Again, not that important, but that would be 288 plus 36. I'm just going to use my calculator, which would be 324. And I believe that 324 is a perfect square, meaning that it has a whole or rational square root, which, what is that? Is that 18? I don't remember. Square root of 324, yeah, is indeed 18. So that would leave us with for some reason the square root got extra long, but that would be 6 plus or minus 18 over negative 6. And so here I'm going to get two answers because the discriminant was positive, and in this case it simplifies to be a whole number, which is very convenient. And to get each answer, I could just split them up separately. So one way I could write that as well, it's 6 plus 18 over minus 6, and the second answer is 6 minus 18 over negative 6. And that would be, of course, 24 over minus 6, which is negative 4. And then I would have negative 12 over negative 6, which is 2. And I would get the two answers to my equation, 2 and minus 4. And returning back to the graph, notice that that is the same answers as I was explaining the X-intercepts, which is obviously a lot easier, but the quadratic formula is awesome because sometimes the X-intercepts are not so easy to identify as they were in this case. Like sometimes the square root will not simplify and it's going to be an ugly, gross set of X-intercepts. And actually, in this case, whenever you get a nice whole number for your X-intercepts, that actually means that there was a much easier way to solve it, which was the original way I was talking about by factoring. So actually that implies that this original polynomial was factorable as we would do in a basic algebra class. So let's just check it out and make sure we can figure it out. But if we were to take the original polynomial and try to factor it, notice actually that this polynomial has a common factor of 3. And you could even factor out the negative. That's a good idea when your leading term is negative, which would leave us with x squared plus 2x minus 8. And I'm going to factor out from the whole thing here because this is not, I'm not applying the same completing the square strategy, which we were doing a couple videos ago, returning back to a traditional factoring where we factor out the GCF and then we, use other techniques. And if you want to review factoring, I will be posting some videos on that later. And I'm sure you can find other resources on YouTube as well if you do feel like you want to review. But it's really not that important because we're going to talk more about this in chapter 3. So if it's been a while since you've factored and you're panicking, don't sweat it for now. But all of that being said, this should also factor. And notice that 8 would multiply as 4 times 2. So I could do x plus 4 and x minus 2 to properly factor that. And remember that after I finish factoring my polynomial, I find the answers by setting each factor equal to 0. So x plus 4 equal to 0 would result in x equal to minus 4, and x minus 2 equal to 0 would be equal to would result in x equal to 2, but I could solve the zeros of those factors, which is by the zero factor property, which we're also going to review in chapter 3. But notice I'm going to get the same answers this way versus this way versus this way. So ultimately, it was kind of like with the vertex formula. If you want to solve quadratic equations, you can use any one of these methods that you want. I generally suggest the formula because sometimes factoring doesn't work. The quadratic formula always works. So it's just kind of better from that perspective. But one of the questions is, well, first of all, you need to have it memorized. But second, why does this make sense? Again, we're going to do that a little bit later.